Good evening, everyone, and welcome to the first monthly meeting of the Astronomical Society of Victoria for 2021. This month we have a presentation by the University of Melbourne Outreach Fellow Clare Kenyon. Claire will be discussing with us the TES Exoplanet Satellite, how it works and the interesting planets it's discovered. The presentation will be followed by Perry's Sky for the Month, and then our telescope and a voucher raffle will be drawn for those of you who signed up during that period of our membership drive. It should be about 9:30, I would say. But for now, let's hear from our president, Mr. Steve Paddy.
Thanks, Mark.
Sorry, I almost called you a peasant.
That's right. The president. Okay. Welcome, everyone, to this special January general meeting or monthly meeting. We don't call them general meetings anymore. Just a few quick announcements before we introduce Clare Kenyon. Before you get your next issue of Crux, I submitted that before the COVID restrictions came back on board. So I've unfortunately said that we're having section meetings back at our lodge. That will be delayed until the restrictions are lifted back to more than 15, back to 30. So I'm sorry about that, but I can only type what I can at the time. The great conjunction that we had at Caulfield Racecourse was fantastic. I attended both nights. One night was clear, the other night was overcast, and I think we had pretty well good numbers for both. Mark, that was correct?
Yeah, I think all up we had about 400 people across the two nights.
Yeah, I thoroughly enjoyed it. It was a very upbeat experience for me, and I think it just shows what we can actually do. LMDSS, it's now open for business as usual. If you need to go up, you have to book via our website and follow the regulations that we have, that you will get about the COVID. We have a new section director for the radio astronomy section. He's Rob Arrowsmith. He's taking over from Clint Jeffrey, who has spent many, many years in the job. I thank you very much, Clint, if you're watching. I'm sure Rob will do a sterling job. And I have noted that you have now moved over to the dark side of visual astronomy. And for those who are wondering what I'm talking about, Clint won the go-to telescope that we raffled at the Christmas barbecue. So that didn't prompt him to give up the radio astronomy, but certainly he has something to look forward to over the coming years. That's all the announcements I have, and I'll now introduce you to our guest speaker. Clare Kenyon is a Labey Teaching and Outreach Fellow at the University of Melbourne, with experience in teaching and outreach programs such as coordinating telescopes in schools, Year 10 work experience, and the Kathmandu Astrophysics School. Claire has numerous YouTube interviews, podcasts, documents, public lectures, and many publications to her credit. Claire is here tonight to give a talk on the TES Exoplanet Satellite, how it works, and the discoveries it has made. Okay, Claire, thank you. And welcome.
Introduction. Thank you so much for your kind introduction, Steve. I'm assuming you can hear me now. Good. Okay. Yeah. So I'm actually going to talk to you. I've changed the title a little bit. I hope you don't mind. I've changed it to Exploring Worlds Beyond Our Solar System with TES. And then an alternative title for you is An Introduction to Finding Exoplanets and the Transiting Exoplanet Survey Satellite. The reason I've changed it to that is because I thought it would be really good to give some, maybe a little bit more background about exoplanets generally, start off the year gently, rather than getting too hardcore into astro straight away, so that we can make sure that all the new members feel welcomed and not scared away. So we're going to actually have a nice introduction to exoplanets first, and then I'll talk a little bit about the TES mission, and also, as you said, some of the cool things that it found, which is I was just so excited reading all about it, and I'm so excited to bring it to you. So let's kick it off. So first of all, we're going to start with some background. I thought we'd start with a little bit of background on me, even though you've given me a great introduction, because everyone says, oh, what's the Levy Teaching and Outreach Fellow? And they're absolutely right. It's not like it says on the tin. Basically, I run a program called Telescopes in Schools, which is like what it says on the tin. We at the University of Melbourne have a bunch of 12-inch and 9.25-inch Meade and Celestron, respectively, telescopes that we put into high schools. We run PD for the teachers to use them, and then the teachers actually run observation nights with their students and their staff and their parents, and we usually send out volunteers to the schools. At the moment, really just doing state schools, but we do some ad hoc visits to schools, although COVID's obviously put a stop to that for a little while now. Part of my job as well is I run the U10 Work Experience Program, something I'm very proud of. We've got somewhere about 90 students now coming through doing streams between astrophysics, particle physics, and also nanoscale imaging. So it's really great to be able to offer back to our U10s, back to our community, some science, and to show everyone how we sort of do it at university. As you mentioned, the Kathmandu Astrophysics School, it's in its third time through now. Our first one was on 2016, was in actually in Kathmandu, which was busy and somewhat stressful, but amazing. We loved it so much we came back and did it again, but we did it in Pokhara this time. This time we've had to split it into 2 schools of 10 weeks, which we're currently on a break digitally at the moment, and then we'll probably try and do a part 2, which is actually in Pokhara again, obviously COVID permitting. As you said, I've written an article here and there. I love to talk to ABC radio. Jacinta's probably a friend of mine now, I think. Always just love to wax lyrical about all sorts of science. And occasionally I am lucky enough to get on TV, which is kind of exciting. And I really love being able to share my enthusiasm for what I do and science just generally with the public. I've also branched into some curriculum design. So this was actually a maths incursion day. And yeah, so they basically put together a video and a stop-start video for the teachers, and also a student and teacher booklet, which they did for the whole morning, basically. And I've had some really good feedback on that, so I'm always looking for new projects, so please let me know if you've got anything in mind. That's on my brand, Red Lips Astro, which is a bit of a side hustle for me at the moment. And finally, I've been so lucky to be chosen as next year's cohort. So it's a 2-year program called Superstars of STEM. They're absolutely amazing. They're all about increasing the visibility of women in the media in STEM. And it's all about making sure that we're really showing everyone that girls can and that we do. So I'm super proud to be part of that program starting this year, actually, 2021. That's the first time I've made that mistake. So there you go. All right. I've done a Bachelor of Science a long time ago. Don't ask how long ago, at the University of Melbourne. It's a nice big circle because I spent most of my time there. I also then did a Master of Science by distance with Swinburne when I was living overseas in Abu Dhabi and also England. And then I finished it off when I came back to Australia. I did some teaching. It's the equivalent of a graduate diploma here in teaching, and I did some teaching actually at a school in Nottingham. And then I, for some reason, enjoyed pain and did my Masters in Education actually concurrently with finishing off my Masters of Science. So yes, I'm a sucker for punishment. I came back home and I actually started teaching in a classroom. So that was 2 years at Glen Ira College. Absolutely loved bringing physics to young people, and then decided that it was time I went back and did a PhD. So that's where I'm at the moment. My personal PhD, I study these things called quasars, or active galactic nuclei. Essentially, they consist of a supermassive black hole, and about 10 or 15 years ago, or 10 years ago when I used to make this slide, I used to make a joke about a band called Muse because they had a famous song, but it's no longer relevant. So I apologise for that. You don't get a nice music song. So supermassive black hole in the centre, surrounded by an accretion disk of material that falls in on the black hole. You've got this dusty torus around the outside, and then you have these broadline clouds, which is basically gas clouds. And my whole PhD basically is that region, looking at broadline clouds, trying to work out how to use spectra and the physics that we know in simulations to actually tell us what's going on in these galaxies that we will never get to see. So if you want specialized, that's specialized. And as you probably worked out, this is not exoplanets, this is galaxies. So today I just thought I'd branch out and do something a bit fun and bring some more, I guess, easier to understand and easier to explain, and certainly something I can be really enthusiastic about today. We've also got narrow clouds and a jet, which sometimes we see as blazars if we happen to be facing down that in the galaxy. So the outline today, I'm going to talk to you about the first exoplanet detection. It's probably earlier than you think. I wish I had a prize to give you to ask you to put in the chat when you reckon the first one was detected. Some of you probably already know, but it's probably earlier than you realise. I'm going to talk to you a little bit about just the main ways that we search for exoplanets. There's actually a large number of them, but we typically use about 5 or 6. And then I'm going to talk to you about TES. So you'll be patiently waiting, and then I'll come up to TES. I'm going to talk to you about a whole bunch of interesting exoplanets and also systems, but also some other observations that TES made that actually weren't exoplanets, but were equally interesting and cool in a science way. And then I just want to have a quick chat with you about citizen science with TES, which you can do from home. So don't let me forget that. All right, so the very first exoplanet. Most of you would be familiar, maybe, with this. This is the 60-inch reflector at Mount Wilson. Many of you will be very familiar with the history of discoveries. So looking at how galaxies, this is where Hubble actually basically made his big discovery that galaxies were speeding away from each other. So that's all related to that Hubble constant you might have heard about before. But interestingly enough, in 1917, a spectrum of Van Manen star, or now called Van Manen 2, it was taken in 1917 by this 60-inch telescope with a spectrograph on it. It actually wasn't noticed at the time. They thought it was just a dusty white dwarf. So Van Manen star is actually the closest non-binary star, a non-binary white dwarf to Earth. And it has these really weird heavy elements in its photosphere. So the photosphere is the outer layer of the star that basically all the light comes from. So we call it a polluted white dwarf. And the theories for how these came about, really, they didn't really know how it happened. But they didn't really think, they couldn't really come up with how these elements got into the atmosphere. And interestingly enough, it took until a lot later, sort of in the 2000s, for somebody to look back and go, actually, inside this spectrum here, and actually system dynamics of exoplanets has actually caught up to our data, that somebody's looked back and gone, hang on a minute, that signature right there, that is an exoplanet basically being pulverized by this massive gravity of the white dwarf and falling onto the photosphere of this star. So interestingly, you could say that this was actually the first exoplanet discovery or detection, but I don't really think it, well, for me, it's probably not the number one because I don't think it wasn't known at the time. So it's quite interesting just to go back in history sometimes and to look at data from a long time ago and to actually see evidence of an exoplanet from 1917. A couple of other potential candidates for the first exoplanet discovery. In 1987, Gordon Walker at the University of British Columbia used a radial velocity technique, which I'll talk to you about in a minute, to detect this Jupiter mass body around Gamma Cephei, about 45 light years away. But the weird thing was it sort of orbited every 2.7 years, which is strange. It's not strange anymore, but it was strange back then. And Gordon wasn't even sure about it. So he came out in 1992 and went, oh, no, actually, I don't think that's an exoplanet. We're still arguing about it. So on the NASA exoplanets page, it still actually has it listed as an exoplanet, but in other sources of material, it's suggested that it's actually a very small red dwarf or a massive brown dwarf. So that could potentially be your candidate. Next, you're looking at HD 114762b, which was discovered by David Latham et al. At Smithsonian Astrophysical Observatory, also by the radial velocity method. It was actually considered really weird at that time, and therefore it wasn't really understood as a planet. It was just a passing reference that he thought, oh, maybe it's a planet. This planet had 11 times the mass of Jupiter, and its orbit was a tenth of the size of Jupiter's. So it was basically what we call like a massive Jupiter, a hot Jupiter these days, or yeah, so very, very warm star and very, very big. And we just didn't really know that they could exist. And to top that off, it had an extremely elliptical orbit. So at the time, in sort of almost the 1990s, the field of exoplanetary discovery and detection and even understanding of the dynamics and evolution was so young that we really didn't even realize these sorts of things existed. And then finally, in 1992, Alexander Volchan, I hope I said that okay, and Dale Frail, I reckon I nailed that one, found 2 Earth mass planets orbiting a pulsar using pulsar timing, which I will also explain to you soon. But does this count? Because, well, it's around a pulsar. It's not really a star. It's a dead star. They weren't formed, these planets weren't formed in the protoplanetary disk that we sort of think of as our solar system formation. So it's a dead zombie star. So does it count? It's been called Lich after a powerful fictional undead creature. And it's actually got 3 planets, I beg your pardon, Draugr, Poltergeist, and Phobator. Somebody got into that romantic style literature there for those names. But anyway, so those are the 3 candidates. I don't know which one you like, but this is actually the one that won the Nobel Prize for Michael Mayer and Didier Queloz. They also used radial velocity. And they found this planet of minimum mass between Saturn and Jupiter, so something in between, orbiting a sun-like star called 51 Pegasi. But the period was only 4.2 days. And as I said before, in the 90s, we really didn't understand exoplanets or dynamics or the variety of planets and systems that could actually exist. So it was actually met with a lot of skepticism. But ultimately, it was found out to be correct, that detection was verified, and it actually forced a revolution in how we look at planetary formation and system dynamics today. This is a hot Jupiter, a typical hot Jupiter. It orbits a star every 4 days. Its temperature is about 1,000 to 1,800 degrees Fahrenheit, which is useless for us, so 538 to 982 degrees Celsius. It's about 51 light years from Earth. So it's usually most people's number one. Yes, this was detected and verified. This is normally what we would say the first one was. Certainly the Nobel Prize Committee thought so. Search projects that have looked for exoplanets in history. So a lot of you would be familiar, hopefully, with Hubble, which started in 1990, and it actually pioneered the search for exoplanets, profiling exoplanetary atmospheres in 2002, where they had a little spectrometer, and they actually looked at the atmospheric composition of a planet orbiting HD 209458. Then we had MOST and Spitzer, both launched in 2003. Now, you might not have heard of MOST. MOST is the Microvariability and Oscillation of Stars, which is a space telescope, took precise measurements of variations in intensity and the brightness of stars. So it's essentially looking for transits. It also helps data scientists probe the atmospheres of planets beyond a solar system. It did suffer a couple of instrumental failures, which probably didn't help. We also had Spitzer, which is one of the great telescopes that we have, so Space Telescope. It's just ended its 16-year observing run in January 2020. It could actually determine the masses and densities of planets. So one of the most famous group is the 7 Earth-like planets orbiting TRAPPIST-1. And it could also look into the thick clouds of dust, looking at newborn stars, so with infrared imaging. So it was a big instrument, and it's sad that it's actually stopped operation. And then in 2006, we've got COROT, which is the Convection, Rotation et Transit Planétaire, or in English, the Convection, Rotation and Planetary Transits, which was basically looking for transits of extrasolar planets, and particularly large terrestrial size, so not gas giants, and also trying to do some astroseismology, so looking at oscillations in stars. You'll all be hopefully familiar with Kepler. Kepler's our space darling. Kepler has found thousands of exoplanets. It's been the most prolific detector to date. The first mission ended in 2013 when the spacecraft unfortunately lost its pointing ability. So it could no longer actually properly point to where it wanted to look. And then in 2014, we had K2, which was actually Kepler reimagined, second mission. Despite this diminished directional capability, we actually still managed to keep going and find exoplanets. And then finally, that brings me up to 2018, where TES was launched, and it's designed to take the reins out of Kepler's hands, albeit in a different direction. Okay, so here we go. So here are the 6 types. I said to you before, there are about 6 types of ways that we use to find exoplanets mostly. There are a large number of different ways to find exoplanets, but these have been by far, well, the only successful ones, and they're also the most widely used. So we're looking at radial velocity, which I mentioned before, and I'm going to go through all of these individually. So we're looking at radial velocity, which is basically looking for wobbles in a star, and a lot of these techniques are about looking for wobbles. Gravitational wobbles. We've got gravitational microlensing, where you're looking for disturbances in a background light source. So something behind is lighting up, and it's going through a gravitational lens, which is the exoplanet system. Astrometry, which is looking for tiny positional changes in the sky and extremely difficult to do. Pulsar timing, which I hinted about before with LIT. So that's actually just looking for variations. Every time the beam sweeps past us, if it's wobbling at all because of a planet, that beam will actually be slightly out of time, and we can detect that. Direct imaging, in 1990, I would have said, no way, we can never see these. But yeah, we're taking pictures now of planets, and I'll show you some of that. And then finally, transits, which is looking for shadows or brightness dips. So we look at the star, we basically stare at the star, and we wait for it to dim. So I'm just going to take you through the radial velocity method. The radial velocity method is basically a wobble method. So essentially, and a lot of you might know this, but even in our solar system, the sun doesn't actually sit there and have the planets go around. The center of mass between the sun and the planets is actually a little bit more complicated. If we simplify it to just one star and one exoplanet, what you can see is that the center of mass of the system, that is the point at which the star also goes around and so does the planet, is actually not right in the middle of the star. So that's because basically the star's pulling on the planet, which we know, but also the planet pulls on the star. But the star has so much more mass that the star doesn't really get accelerated very much. It doesn't feel a big force, but there's still a small force. So that little point that they're orbiting around at the moment, we call the barycenter. And this this wobble forms the basis of many of our exoplanet finding techniques. So what happens here is a lot of you will be familiar with Doppler effect. So if you're standing on the street and some rude person is beeping their horn, they're just holding it down, and they come towards you with the horn on in their car, and then they drive away. What you've experienced is the pitch rising, where the wavelength's actually getting smaller or the frequency is increasing as the car comes towards you. So when you've got motion in your line of sight, and actually as it's going away, you start to get a longer wavelength, and it sounds like the pitch drops, so the frequency is actually decreasing. This happens with light as well. I'm sure many of you will be very familiar with this. When something is moving towards us and giving off light, the color of the light gets blue shifted. And when it's moving away, the color of the light actually gets red shifted. So if we're looking at a system where there's a star and a planet, when the planet's coming towards us, so when the planet and the star are coming towards us, those wobbles, we can actually see in the spectrum of the star that it actually shifts to the red, to the blue. And then when the whole system's wobbling backwards, it's shifting to the red. So this is called radial velocity, and it is one of the most popular methods. This method can be used to indicate the presence of planets, obviously, so it can detect the planets, but it can also look at the number of planets and also look at their mass. So because it is a mass method, it sort of gives you all of those parameters that are in those sorts of mass equations, I suppose, if you think about it. So we found 826 planets with this method, and some popular ones, popular missions that have used this method. You probably know Keck, you might know LIC, and La Silla in Chile, and there's always more going out. This is by no stretch a exhaustive list of missions. Okay, so the next one I'm going to talk to you about is kind of cool. It's called gravitational microlensing. And to me, it still feels like it's new age and wacky. But essentially, it's gravity lensing. So it's lensing just like any other type of lens. So even a glass, if you wear glasses, or if you've used a magnifying glass or anything like that, that's a lens. But lensing by gravity, the idea is basically that masses actually, sit in space-time, and they curve space-time. And the light actually travels along these curves, not necessarily in a straight line. So when you see the planet and the star go past, it happens to go through one of those line of sight to the background source. So that little yellow and green sort of smarty looking thing is the system that we're talking about. When it passes between the background source, which is this light, and us, we get this little blip. So if you have a look at that little light curve down the bottom that's going up with light and time, you'll see a tiny little blip as that caustic, as that light string goes past the planet, and then we see the bigger one, the smooth one that goes past the star. So that's actually a very fine signal that we've got exoplanets. So this is a telltale blip, and we found about 106 planets here. There's a big network called the Korea Microlensing Telescope Network, and you might have heard of OGLE. This is a really rare and random method. So you really just have to be looking in the right place at the right time, and it doesn't repeat because it'll never pass by your line of sight again. Well, not unless you get very, very old and it's, older than probably the galaxy to go around. Anyway, that's not me. So the next one is astrometry. So this is actually one of the oldest methods of detection in astronomy, and it is in fact the first one that we really thought about using for exoplanets. But the problem is it's really, really hard. What it requires is looking out into the sky, finding other points nearby the star that we want to see the wobble of. Remember, the wobble is because the planet is actually pulling on the star a little bit, so the star's wobbling. We have to make very precise measurements of the center of that star, of the center of brightness. And we actually have to compare it over time with nearby stars that are also basically stationary. So this is a really difficult method, very, very, very difficult. And because of that, we've only found one. There are observatories at the moment using this method to find them, Gaia, and then there's a Paranal, and then there's a couple more coming online. So that one star has got the extremely wonderful, memorable name of Dennis P, J082303.1, and then it's basically its right angle and declination coordinates. It's not even special enough to have a name like Lich. The next one I hinted about before, and that's pulsar timing. So basically, when pulsars go around, they have a jet out of their pole. So when they spin on their axis, that jet sweeps across Earth and we see a bright flash. Pulsars are incredibly regular with their flash as they go around. So if we know the timing of a pulsar and we look at it, the wobbling of the star from the planet actually causes that timing to just go a little bit skew. And so it's a really sensitive method of looking for exoplanets, so it's quite good. But pulsars are quite rare generally. And it can actually go down to about 1/10 the size of the mass of Earth. But as I talked about earlier, generally we're not that interested in finding exoplanets around pulsars, at least not from the sense of looking for life or looking for habitable planets. So in some ways, I think there's probably less interest in finding planets through this method. So we've had 5 confirmed systems of this, and you probably would be familiar with Parkes and also Arecibo, of course, which unfortunately had an accident and no longer with us. So yeah, basically the other good thing about this as well is that you use it in the radio. You don't have to be using light for like what we're going to talk about in a minute with direct imaging or infrared. So you're not really that affected by the Earth's atmosphere. So that's another positive. Direct imaging. Now, this is really cool. This is what I thought would never happen. Never say never. So we basically need to, so if you look up into the sky and it's a really bright day, often you'll like cover the light source with your eye, or if you're sort of sleeping and someone wakes you up, the first thing you do is put your hand over the glare of the light so that you can see the light around that source. that's basically what we have to do for direct imaging. We need to use what's called a coronagraph. We actually use it to image the outside layers of the sun as well. So when we're looking at like the chromosphere or the corona, or the corona of the sun, sorry, not the chromosphere, the corona, and then all the way out, when we're looking for flares and prominences, basically you'll see a coronagraph put on the surface, well, over the circular part of the actual sun, so that you can look at the side. So the coronagraph basically blocks out that glare. This image at the top is a movie of 4 real exoplanets. So this is imaging, this is real imaging, in orbit around a star, HR 8799. This is 7 years worth of images from Keck in Hawaii. And I just think it's really, really cool. There are other ideas about taking this into space. So what you're looking at in the top there is actually a star shade. So the idea is it will unfold and actually block the light, just like a coronagraph would do, to about the size of a baseball diamond, believe it or not, and then actually look for signatures in the atmosphere of these exoplanets even. So we're starting to really, really just advance what we're doing at a crazy rate. We've found 51 planets this way so far. And some of you would, well, hopefully you're all familiar with the European Southern Observatory and Keck and Paranal, and actually Gemini, which is always holds a nice little place in my heart because that's where all my data from my PhD came from. And finally, we're up to transits. So you're going to need to remember this when we get to all the information about TES. Now, transits, we're not talking about sort of the American word for transport, like public transport. We're talking basically, is very similar to things like eclipses. So just like when we have a solar eclipse, which is basically the sun, we're looking from Earth and the moon passes in between, we call that a transit. And some of you might have actually even seen transits of Mercury before, or even Venus in front of the sun. So anything that goes between our line of sight and the background source of light, in this case, stars, we call that a transit. So transits are actually, all we have to do really is stare at a star, take good measurements of how bright it is, and then look for dips over time. Now, the sizes of these dips, so the depth of these dips, say that 20 times quickly, will actually tell us a little bit about the planet themselves. So if you think about it, the depth will actually be related, so how much light is actually blocking out from that star will be related to its relative size against that star as it passes. So you'd expect planets with a large radius to actually block, relative to the star, to actually block more light. So for example, this one going across is quite a large radius. It's supposed to be, in this simulation, supposed to simulate a large radius. And you'll see the light dip on the left there in the light curve. This one has a smaller radius. And then it's also complicated by the fact that the third one joins in on the party. So there is an equation for this if anybody's interested. It's basically the radius of the planet when we detect it is equal to the radius of the star times the square root of the transit depth. So that depth there that you're looking at on the left is what we call the transit depth. The other piece of information we can get from these light curves, of course, is how long it takes the star to go across the face. So this actually gives us 2 pieces of information. Now we get a radius of the planet and we also get basically some orbital parameters. As with every other exoplanet detection and survey mission, really what we'd like to do is couple these with each other. So for example, you might have heard of TRAPPIST-1. There's 7 planets actually orbiting a star. The fact that we can see these, the light dips happening here, the equivalent light dip for us to see TRAPPIST, which is 100 trillion kilometers away from Earth, it's the same as us seeing a fruit fly pass just in front of a car light. So that's the sort of dip we're detecting when we're doing these sorts of transits. So we need really sensitive equipment, but luckily technology has come to save us. So we've found, not me personally, Kepler has found the bulk of these, so 3,287 confirmed planets. And I've mentioned some before, Kepler, Corot, and TES are obviously use this method quite exclusively. So a little summary for you. I don't expect you to read all of these, but basically what I want you to take away here is that for ones that use wobble, we often get things like mass, or we get orbital parameters like radius, because those 2 things actually dictate the gravitational force. For things like transits, we get radius of the planet. So it's best if we can use detection and survey using one method and then follow it up with another survey to find the other things. And then we start looking at blocking it out and looking at atmospheres, which I'll talk to you about hopefully in a minute. But yes, so basically there are 6 ones. TES, which I'm going to talk to you about now, hopefully you'll work out what method it uses. It is on the tin. So TES is the Transiting Exoplanet Survey Satellite, and it's probably one of my more favourite astronomy acronyms. It's not hard to see how they got the acronym, and it's not very forced, and it's quite nice to say. So TES was actually originally an MIT initiative, and then they basically went to NASA. They got knocked back a couple of times, and then NASA took them on, and now it's an MIT-led NASA mission. There's a whole bunch of sharing going on there. We've got NASA, we've got Orbital ATK, you've got Smithsonian, so we've got the SAO doing some stuff, and Goddard Space Flight Center, which a lot of our videos come from today. And yeah, so there's a big collaboration here. It's not a small thing at all. It took the reins from Kepler, and I will actually compare Kepler for you with TES in a minute to show you the difference in the missions. But it took the reins from Kepler, Kepler passed the baton on to TES, but the carriage is basically being driven in a different direction. TES overall was designed to look for small planets around nearby bright stars. And I hopefully will mention to you shortly why that's really important. Here's a cool video. We all like seeing launches. Well, I do. So this is actually the launch of TES. It went up on April 18, and it was on 2018, sorry, as a SpaceX Falcon 9 rocket from an Air Force station in Florida. Now, I actually find this really interesting because this is another marker to me that space flight has really started to become commercialized, and also people are starting to see reusing and recycling as something that is actually commercially viable and also something to aim for. So this went up on a Space 9 rocket. It has a highly elliptical orbit, so it's actually quite novel for TES. So once it was in its final orbit, so it did a bunch of maneuvers, and then it's in its final orbit, that blue line there is TES, and that white line there is actually the moon. So it has an apogee of about the distance of the moon, so its furthest distance, and a perigee, so a close distance of 108,000 kilometers. Now, TES orbits Earth twice during the time that the moon orbits the Earth. So we call that a resonance. It's a 2-to-1 resonance with the moon. This orbit is actually expected to stay stable for 10 years plus decades. Just because of the way it is 2-1, gravity's not really affecting it, and it's highly elliptical. So I'll talk to you about how that all works in just a minute. So TES's first light was August 7, 2018, and this is actually the strip of stars that it captured. And so TES actually was looking in the southern sky first. So TES was a mission that went for 2 years, and the southern sky was the first year of its operation. So this is the first light of our beautiful southern sky, and you'll probably recognize some of those labels in there, particularly the Large Magellanic Cloud. It's one of my favorites. And basically what you can see here is this is combining the view from all 4 of its cameras. And this is a 1 30-minute period taken on Tuesday, August the 7th. So you can actually see the large and the small Magellanic Clouds down there in the bottom right, and the Tarantula Nebula, which is always a good little target for our 12-inch MEADS. And there's a globular cluster, and then the brightest stars in the image are Beta Grus and Doradus, and that actually saturated the entire column of the camera detector pixels on the satellite's 2nd and 4th cameras. So accidents happen, but I guess this is why we take images to calibrate. So the actual mission for TES, so as I said to you, it started off in the southern sky, and what happened is the southern sky was divided into 13 sectors, and these sectors were monitored for about a month each. It actually saw other things during this time, like supernovae and comets, which was really cool. And at the end of its year surveying the southern sky, we got this beautiful panorama, so a mosaic panorama. You can see in the middle there, when if it replays, it'll replay in a minute. You can see in the middle there, there's actually something called the continuous viewing zone. So that's the place that it overlaps the entire time. So that area above the pole, basically TES was looking at for pretty much the whole year. You should have a look at this and really appreciate the detail with which TES has captured our sky. Considering that it's a bunch of mosaics all just put on top of each other, stacked images, I think it's absolutely fascinating to see the detail of the LMC. And basically, TES was here. The reason TES exists is to go and look at about 75% of the entire sky. So like I said to you, started off in the Southern Hemisphere. The next year, in 2019, it focused on the Northern Hemisphere. The really great thing, so TES was charged with looking at around 200,000 of the most close or nearby stars to Earth. These stars were picked based on the majority of Keplers, so on basically to look at ones that we thought would have exoplanets. But the great thing about looking for these stars, which were G, K, and M type stars with apparent magnitudes brighter than a magnitude of 12, the great thing about looking at these guys is that they're close to Earth. So remember what I said before about wanting to use a detection technique and then use a different technique to investigate the planets further. If we pick stars that are bright and close to Earth, then we actually can use ground-based telescopes to get more information about these exoplanets that we have found. So TES was actually designed to be completely different to Kepler. That's all I need to say about that, I think. There we go. So so just back here, if you look here, like I was saying before, with all of these tiles here, so that's 1, 2, 3, 4 cameras stacked, and that top part there is that continuous viewing zone that we were talking about. So the satellite itself, for any of you technology people, it had 4 wide-angled telescopes with CCDs on them. So it had a 24 times 24 degrees viewing. It was designed and built by MIT's Lincoln Lab in Lexington and the MIT Kepler Institute. It was basically had 2x2 CCD arrays arranged in a square. It's a total of 16 megapixel per camera and a total of 16 CCDs. The pixel scale is about 21 arc seconds per pixel. So I think you can agree that it was pretty awesome. And what you saw before was a result of that. Each of these 4 cameras had, as I said, 24 by 24 degree field of view, 100 mil effective pupil diameter. And actually they had to design it so that it was athermal, so it could deal with heat. It's looking at a wavelength range of between 600 and 1,000 nanometers, which is blue light that we can see all the way down to the near infrared. And finally, 50 parts per million photometric precision on stars with magnitude 9 to 15. So the actual mission. So the idea here was that TES would survey a patch of sky 24 by 96, because of course that's 4 times 24, for 2 lots of the orbit. So remember, TES went round its orbit in 13.7 days. So TES would stare at the same patch or segment of sky for 2 lots of 13.7 day orbits, obviously started in the Southern Hemisphere, with 2-second images. It would cut out all the bright stars and then stack them, but there were also 30-minute stacks of full frames as well. There were 26 segments, as you can see, in the first mission of operation, and then they did the same thing in the Northern Hemisphere in the second year. What else was I going to say? So it's looking at about a brightest 100,000 stars at a 1-minute cadence on average. So the continuous viewing zone actually meant that we were able to, TES is able to look at the sky permanently, basically, for 11 months. So long enough for the other ones for us to see exoplanets in the other parts of the segment. But that continuous viewing zone is actually really important for some of the things that we found. Well, TES found. I say we, but I mean we as a science community. I'm sure you all know that. I want to compare Kepler and TES. Now, most of you would know about Kepler at least a little bit. Kepler is prolific, discovered thousands of exoplanets, more than 2,600, whereas TES so far has found 66 confirmed exoplanets And that should actually, the comma is in the wrong spot. It should say 21, it should say 2100, not, well, it does, but the comma's in the wrong spot there. So it's 2,100 candidates that they're still sifting through this data. The great thing about this large field of view for TES was it could actually detect a lot of them at the same time. So Kepler was basically there to determine the frequency. So how many times do we find Earth-sized planets? How common are they? Kepler looked at a very small part of the sky. So 0.25% of the sky at a time, very, very, very small. And it looked really deep, very far away and really deep all the way through space. That's completely different to what TES did. TES looked at the whole sky essentially. So by the end of its primary mission, it had actually covered 75% of the sky. And also, the thing with Kepler was that because it was looking so deep, the bulk of these stars were between 100 and 1,000 light years away, which means that the ground-based follow-up for other surveys was actually really difficult. TES is only looking at stars of up to 200 light years away, so we can actually follow up on those detections pretty quickly. These stars are also really bright, 30 to 100 times brighter than Kepler. So some of the things that I really loved when I was looking at all of this stuff about some of the things that Kepler, that TES has found, I've divided them into two sort of things. One is sort of dynamics and planetary systems, and the other are actually just cool exoplanets. So I'm just going to briefly take you through a few. This is super hot, Kelp 9b. When I say super hot, I mean it. It's actually hotter than some stars, the surface of some stars. And the actual star it's orbiting is quite young. It's only about 300 million years old. Now, why is it so hot? Well, it's tidally locked, so it faces the star, the same faces the star the whole time, meaning that side's going to get really hot. And it's orbiting really close, okay? It's got an orbital radius of 0.035 AU. And AU is, of course, the distance between Earth and the Sun. So it's orbiting 0.03, so 3% of the distance between Earth and the Sun. So it's really, really close. So the dayside temperature on this planet is about 4,300 Celsius. It's quite close, so 670 light years away in Cygnus, but, you know, I don't really want to go there. The atmosphere seems to be puffed out, so this extreme heat makes it really puffy. And it looks like it's not going to have hydrogen gas in the atmosphere on the star side. They're actually going to be ripped apart. So it's just way too hot for anything to be happening. What's kind of cool is that what's even cooler about this is that the host star is weird, right? The host star is about 2 solar masses. So it's 2 lots of the sun squished together, and it's about 56% hotter than the sun, okay? It rotates really rapidly. It just turns. It turns 38 times faster than the sun, and that's one rotation every 16 hours. So this is a huge star just spinning. What happens to that is it means it becomes oblate. So the poles actually get squished out, and the equator actually gets flattened. So what happens? The equator gets widened. My bad, and the poles come in. So when that happens with a star, it causes something called gravity darkening. And what this means is the poles become really, really, really hot and really bright. And Kelp 9b actually orbits its star in a polar orbit. So not only is it already hot and close, it's actually going around the pole of this star. These two factors combine to mean that every time Kelp 9b goes around its star in about 36 hours, its 36-hour year, it experiences 2 winters and 2 summers. Now, I say winter, but I don't really think it's going to be cold. I think it'd still melt. So that's super hot Kelp 9b. I think it's absolutely awesome. It also has given us some food for thought about how close these things really can be and how relationships can actually be with stars, with their host stars. Bring you to a circumbinary. So TOI 1338b goes around 2 stars. So it's actually the first detected planet going in a binary star system. This planet's about 6.9 times the size of Earth, or between the size of Neptune and Saturn. It's the first circumbinary planet ever found. It orbits 2 stars, and it was actually found by a high school intern looking through the data for transiting stars. So this was actually found by somebody who isn't sitting at a desk in an academic university, which I think is absolutely amazing. It looks like it's a single planet at the moment, and it accompanies one star of about 1.1 solar masses and a cool and dim other star of about 0.33 solar masses. These stars actually eclipse each other. So we see dips in the brightness over here, which you can see down at the bottom. You actually see the dips from the stars eclipsing, and then you actually see the little signature of TOI 1338b. Because of the weird angle of the line of sight of TOI 1338b, unfortunately, we will lose it in November 2023, and we won't get it back again for 8 years. So we won't see this eclipse again until 2031, or this transit. Now I thought I'd have a look at planets that are a bit on their way to being Earths, maybe alternative Earths. This one is the first Earth-sized, well, technically super Earth, I suppose massive, but Earth-sized in radius planet detected by TES. And it was the one that showed that TES could do it. It orbits a K-type star with about 70% of the sun's mass, and with an orbital period of about 7.8 days. It's potentially a rocky planet. It's probably very, very close to the star. It goes around the star in just under 8 days. So it's very, very hot and very weird. Surface temperature is probably around 427 degrees Celsius. So I'm in no hurry to go there. A super Earth, so TES actually observed the transit of GJ357b, which is not the one that I've listed there. So GJ357b was observed by TES, and then actually when they went to follow up the 357b observation, they landed and they found C and D. And what's really interesting about D is that it actually looks like it may be in the habitable zone. So even though this planet's size and composition are unknown at this stage, it could potentially be a rocky world because it does, we're able to sort of work out its mass. And it would range from about 1 to 2 times Earth's size. So it's kind of exciting. It may have a dense atmosphere to have, could be warm enough to trap heat. It could have liquid water. And as I was saying before, being not so far away means that we can actually start looking at these things in greater detail quickly. And finally, for my habitability, we've actually found an Earth-sized one in the habitable zone, which is TOI 700d. There's actually a system of 3 planets. They all seem to be tidally locked to their host star, so they show the same face all the time to their star, which is not like what we would be used to. But it's the first Earth-sized world in the star's habitable zone. It actually orbits a red dwarf. And what's interesting, I think, about it is when we start looking at how much energy that planet actually has, it gets about 86% of the energy from its star as we do on Earth from the sun. It looks like it's actually very, very close to the Earth's radius and a little bit heavier. So these are the, oh no, I'm just going to skip through that. So they've actually done a whole bunch of modelling on what the surface could possibly be. Why do they want to do that? Well, it's not just for fun. Basically, if we want to have a look to see if they've got any atmospheres, we need to know what we're looking for. It'll actually change the temperature on the planet a lot, depending on whether it's got land-covered modern Earth sort of style or an ocean-covered early Mars but with higher density. So which one's correct or which one of 20 is correct means that when we want to go and have a look at the atmosphere, we really need to know which chemical signatures we're looking for in order to make sure we pick the right instrument. So this is why they're doing modelling, not just for fun. But basically, we're going to be looking at this definitely when JWST gets up there for signatures of atmospheres. So I think that's absolutely really cool and probably our best candidate at the moment for the exciting things that we all want, hopefully, which is potentially just looking for another habitable planet. So other things that TES caught supernovae, TES caught comets. So this is actually a comet going through the field of view in a bunch of asteroids. And TES also caught an exocomet. So there's actually a trio of exocomets in the Beta Pictoris system. And because TES is just looking at the sky at all of these stars, it catches this stuff. Yeah, I love it. And the one final thing I'm going to mention, which is just so cool, you probably know what a tidal disruption event is. If you don't, that's okay. Basically, if a star gets too close to a black hole, the star starts to get spread out. It bursts into a million pieces. The gas flies off. and as it falls into the black hole. Now, we can actually detect this now through gravitational, through gravity waves, but this is actually this was detected by TES. And what's really interesting about this is TES was just staring at it. And it's like, it got it for the first, it got it so early. So it was just sitting there. It got it from start right to end, which we really don't really have that sort of data, because typically the missions that are looking for this sort of thing are scanning the sky randomly, whereas TES is just sitting there waiting, looking at other things. And it just happened to notice this event. So this is affectionately Assassin 19BT, and this was found on January the 29th. And basically it got follow-up observations straight away from ESA and Las Cumbres Observatory. It was in the continuous viewing zone. So that was what I was talking about with that little polar area. And so basically they saw it from beginning to end with no movement at all. It actually gave us the earliest UV measurements for a tidal disruption event to date. And also it looks like we got some really good temperature data for this, and it seems to have decreased really, really rapidly. These are so rare. I can't tell you how rare these are. Well, I can. They're about 100. They're about 10 to 100,000. So 10,000 to 100,000 years, one happens in galaxies like our Milky Way. So to get this right from the start to the end is an absolutely incredible event. Finally, I just want to say citizen science is alive and well. Originally, we had test data here, and I think this was more probably for kids, Planet Patrol. But if you are interested at all in getting onto some citizen science in Zooniverse, which they run a whole bunch of citizen science, you can actually troll through the data for tests and actually help astronomers work out whether they are whether there is an exoplanet or not. So with all with all data, obviously we have algorithms and we go through and we check and we want to know whether it is or it isn't something. But sometimes you just need a pair of eyes. So you can actually get on there and do it. They're about 7% through. So if you're keen, this is good sitting down astronomy, not even cold. So you just sit there and just have a look, and you go through, you go and you get, it's a bit like if anybody's ever done their Galaxy Zoo classifications. You have to go through some calibration, you feel like you're being tested, and then they let you out into the zoo and you can actually help find exoplanets. So I just thought I'd pop that up there if anybody was interested. I'm pretty sure you can just search for this, but it's called Planet Hunters Tests. And so there's a summary. I'm not going to read it out to you. I feel like I've spoken now for 53 minutes, so I think it's time for other people. But I'll leave my summary up for you.
Thank you, Claire. That Zooniverse, is it Test Zooniverse link, if you could send that through to me, I might share that on our social media and also email it to our members as well.
Can do.
Wonderful. We have a couple of questions from earlier in your talk when you posted about the technique where you found one exoplanet. Is that enough to have confirmation that the method has worked? I would think a higher number would be required from Lee.
Well, I think the method works, both in theory and clearly has worked once. It's still more successful than the methods that we haven't got any detections at all from. But you're right. I guess in science we like to have multiple, we want to do things more than once, so to show that we can. But I think to break the ice, if you've done it once, I think it can be done. It doesn't necessarily mean that it's a great method. But as I said, it's really difficult. It's probably the hardest technique that we have. But potentially, if we can keep going with our technological advancements and instrumental advancements, we could potentially get quite good at it. So it's worth looking at, but it does sit in there with the 20 or so other methods I didn't talk about. Yeah, so it's not my favorite. I would go transit every time, but you know, it's at least another piece of information.
So we have another one from David. Why would we look for planets near a pulsar? Would the precursor supernova to create the neutron star destroy any planets in the system or leave them uninhabitable?
Yep, so it's quite interesting that you asked that. In fact, when I was doing my master's, I did a project where we did some simulations with planets going around stars. Well, actually, they were just stars, but we lowered their mass. And I actually looked at when can a planet hold on to their stars? So looking at migrating star, when can a star hold on to its planet? So looking at planetary migration, so can they come in towards the star to stay in the habitable zone? And the only times I really found that happened, well, was basically smaller stars. So they're the ones that became red giants. Basically, in the making of a pulsar, we're looking at an incredibly energetic explosion, and I would say definitely not. Those pieces of rock, as I was saying, I think I mentioned that they were not formed in the protoplanetary disk. They're just rubble and material that's actually been brought in later. So whether or not they're planets is really open for debate, and I guess we can all wait for the IAU to change their mind on that one too.
We have one more. From the ASV librarian, Barry. Barry Cleland would like to know how many exoplanets have been discovered, and do you think there are planets around all stars?
I don't reckon there are planets around all stars just because you only need one star not to have planets for that not to be true. And I just feel like the odds on that are a little bit low. Interestingly enough, there is actually a planet found by gravitational lensing. This is not your question, but there was a planet found by a gravitational lensing technique that actually doesn't have a star. So that just got found through a gravitational anomaly, which I found really interesting. I actually wrote down this number today because it is changing a lot. There's 4,324 confirmed exoplanets and 5,708 candidates. Now, it's really important. We call them candidates until they have actually been verified, which is fair enough, because it is actually quite easy to muck up a star crossing in front of a star, so a binary, to think that that's a planet. Or also some stars actually have cold spots. So when we're looking at transits, if we see a cold spot go around in front of the star, we're going to go, oh, it's a planet. So we call that a detection, but then we go, we call it a candidate, but then it's not confirmed until it's confirmed through another technique usually. So 5,708 candidates in a total of 3,209 systems. So I hope I was ready for that answer. I was like, I need to know this number.
We have one more that's just popped up that I think is very important. Claire, one of our YouTube viewers, is there any suggestion for starting undergraduate students in University of Melbourne interested in astronomy? Would like to know some more detail about the last research at the astronomy field. So someone is interested in studying astronomy. How would they go about it?
I'm probably not the best person to ask. I did actually start my degree at the Conservatorium of Music at the University of Melbourne, but I found my way. So I think the best thing to do is always to just be interested and keep learning. That's just me on how to survive life. But also keeping your hand in mathematics. So making sure if you're going to do high school, if you're in high school, you probably want to try and do your maths and keep up your science where possible, physics and chemistry. Some universities do undergraduate astronomy courses, and it's actually part of the major, whereas other ones like the University of Melbourne, they do astronomy as part of physics. So there are actually astronomy introductory topics in first year for the University of Melbourne. And there's also, it moves on, we've started looking at putting second and third year subjects in there as well that are more specific and more focused. But certainly if you want to get into astronomy or astrophysics, physics is your friend, maths is your friend. And also, just keep interested, go to talks like this, meet people, and never be like, you just put it down as a preference. Go and try a subject. There's also a bunch of free subjects as well that you can do. There are some excellent YouTube lectures out there to keep you to get interested. And then sometimes there's some free or sometimes for a cost summer schools and things like that, which you might want to attend. So there's a bunch of ways. But as I said, I'm not necessarily the poster girl for sliding right in correctly.
There we go. David Onions just suggested Open University's Astronomy and Black Holes, a very good entry-level astronomy unit. So
perfect. That's kind of what I was thinking.
That's one that everyone can do.
Yeah, brilliant. Yeah.
Steve.
Okay. I think that's enough questions for now. Claire, before we thank you for your time, it was absolutely a fantastic topic and I thoroughly enjoyed it. I've read a lot on that subject, but I'd like to just give you a short little story. Back in 1991, I went over to Lowell Observatory to meet astronomer Brian Skiff. He was a good friend of one of my Canadian mates, and he was doing research at Anderson Mesa Station on high-resolution photometry of stars. He showed me some of his light curves, and I said to him, "You're not imaging any variability, you're actually imaging sunspots." And he sort of nodded his head and said, "Yes, I am." I just can't help thinking now, could that data be actually showing some large planet body instead of sunspots?
Well, if we're finding effectively what are sunspots on other stars and mistaking them for exoplanets, then there's no reason the reverse couldn't be true. Probably, maybe. It's definitely worth digging that out. Just like looking at the 1917 stuff always, brings up new things to see and to think about. So I would definitely encourage someone to go back over that.
A lot of data.
That's okay. We've got big data now. It's fine.
Yeah. Okay. Well, look, thank you very much, Claire, for a wonderful talk, and I wish you well. And again, thank you. We can't give you an applause, but thank you very much for your attendance.
Thanks very much.
Okay, Mark, if you'd like to take over.
I'll bring Perry in. So we're going to do Perry's Sky for the Night now. And following that, we'll do the raffle draw and run through the list of new members.
Excellent. Good evening, everybody. And I'll also, like Steve, thank Claire for this fabulous, fabulous talk. I thoroughly enjoyed it. And you never stop learning. There's always information, even though I've been with Steve's been with the ASV even longer than me, if that's possible. But in the 30 years of knowledge, there's always something new that you can pick up from a fascinating talk such as the one Claire gave us this evening. So thank you, Claire, once again. Also, just before I get going, and Steve mentioned a very successful event at Caulfield, on a much smaller scale, I'd like to say we had a terrifically successful event last night because the skies have been clear. And that's been the case for the last few nights, and it's also the case for this evening. Last night I was running a session with the help of some other guys that I'll thank in a moment, called Learning to Use Your Telescope Successfully. Mainly aimed at newer members that have perhaps just received their telescopes as a Christmas present. And we certainly had a great range of telescopes, some of them exceptional instruments, others had a little way to go to become really good instruments. But as I said last night to everybody that was there, every one of those telescopes was much better than what Galileo had back in 1610. So there was no excuse for not using them and trying to get the most out of these particular instruments while you still had them. We had about 25 members and 5 people from the ASV helping out. I'd like to thank Mark Justice for being able to get the pickets and the fencing that's required by COVID-safe restrictions, and for also putting them up and helping out through the evening. My thanks also to Stuart Beveridge, Chris Rudge and Ken Lamarquin for coming up in the second half of the night and helping people aim their telescopes and figure out what's going on and how to get stuff in the middle of their eyepiece and aligning finder scopes and collimating and that sort of thing. And also brief thanks to Mark here, Mark Iscaro, for organising the QR coding for the event so that we were nicely legal and there were no issues with COVID restrictions. So thank you to Mark. Now we we'll probably run another one of these events. Normally, I only have time to do one of these per year, and during my holidays in January. But this year, after a few conversations with Steve, our president, there's every chance we're going to run a similar event of learning to use your telescope for newer members up at the Messier Star Party at our dark sky site in Heathcote. So we will send out a message of some sort. You can register for it. You will bring your telescope. There's no sense learning on somebody else's telescope. It's hands-on for the people that are using their own instruments, because after all, that's what you're going to be left with to be able to use from night to night. And the secret to success in this, as I said to many of the members last night, is don't just do it on one night. Go out there and do it again the next night and the night after that, so that you can reinforce the learnings that you picked up at the session. All right, let's have a look around at the sky for what's going on in the next few weeks and month. And by the way, Steve's going to mention it a little bit later, I'm sure, but what a fantastic result to have 130 new members join the ASV since the last monthly meeting back in January. That's a fantastic thing.
Back in December. Since December.
Yes,
since back in January.
Oh, well, my apologies. So the time between the December meeting and today, the January meeting, having that many people join the ASV is something I never thought I would ever see. But now, Mark will help me through this if I don't get it up. Share screen.
Yep.
Then press the button. Is the screen being shared or?
Not yet, no.
Nothing as yet?
No, not yet, Perry. So you've got to go down to share screen. I'll walk you through it. So share screen, you got to click your application window and then choose the application you'd like to share. There we go. We got it.
Fantastic.
There we go.
Thanks, Mark. Let's
no worries.
That screen. Maybe go up a bit. All right, so this is the current time as we are looking towards the south, and that's not really where the action is just right now, but it's a difficult piece of action. So you're going to have an opportunity to have a look at this tomorrow night. We've already had the very, very close conjunction of Jupiter and Saturn. And there's been some fabulous photographs of these. I recently saw one from Russell Cockman, and that was a great shot. That was only 2 planets. If we look down at the west right now, not only do we have Jupiter, we have Saturn and also Mercury. So if you want a challenge, and this is very challenging, because it's still going to be way before astronomical twilight and within a half hour after the sun sets. But tomorrow you'll be able to photograph 3 planets or to observe 3 planets in the western sky. If we zoom in a little bit, let's see if we can center one of them. Let's center Saturn and go in and have a closer look. There it is. So the angle of the rings are such that they're kind of pointing down towards the horizon at this time in its journey from the eastern sky to the western sky. Zooming back out, we also have Jupiter up here. We'll center that and zoom in. And there's Jupiter and 4 of the Galilean moons, which Galileo saw back in 1610. This is probably, no, it surprised me. This is Callisto. This might be Io over here. It is Ganymede. And is this Europa? It certainly is. Now, keep in mind, Europa is a good candidate for some, perhaps not sophisticated, but some type of life to be found under the ice of its global ice shelf in the oceans underneath. The ice goes for about 7 to 8 kilometers, and from there on, it's ocean for perhaps another 20 kilometers. In fact, there is more water on this moon Europa than all the oceans, lakes, seas, rivers, and my bathroom on planet Earth combined, and Europa still has more water than that. So let's zoom back out, and as I always say, water is incredibly important for life, because without water you can't make coffee. Let's zoom in on Mercury and see what sort of phase Mercury is going to present us. Because it's on an inner orbit to us, closest to the sun, it goes through phases, and this is more of a gibbous phase here, I suppose. If we were to follow it, it's centered already, but if we were to follow it over the course of its apparition, we would see that it will grow closer to us, but also it will have less and less of its surface being shown to us, because it's getting to more of an angle, much like the first quarter or last quarter moon. So Mercury goes through much the same sort of phase as what our closest celestial neighbor does. So let's now backdate it to where it was. Let's see what the date is. Currently, the date is going the wrong way. My apologies. The 9th. And so this tight little circle, or triangle if you like, the distance from Mercury to Jupiter is 3 degrees, and about 2 degrees to Saturn. So you will easily fit these 3 planets, if you're quick enough before they set, in the same field of your binoculars. Zooming back out, let's see if we can go to the eastern sky, because the other piece of action that's going on is in the morning sky with Venus and the moon. So I will advance the hours and you'll see it grow darker, and these stars will climb higher. That, by the way, is Sirius, the brightest star in the sky, the belt stars of Orion there, the Orion Nebula here, Betelgeuse, red supergiant, and Rigel, the blue supergiant. But let's get to the morning sky, and I'll get through. There's the moon coming up. The constellation Scorpius is right here. The head of the Scorpion there. Antares, the red supergiant, the heart of the Scorpion. The tail winds around here, and the stinger is G Scorpii. If we advance the time a little bit more, the minutes, we will soon see that Venus is rising as well. Now, that's for tomorrow morning. There will also be another photographic opportunity here. How much success you have, I can't really say, because again, it isn't going to be a very dark sky, but Venus is right near 3 Messier objects. And if I zoom in somewhat, you may be able to see them. There they are. So there's the Lagoon Nebula, M8. There's the Trifid M20, and over here is M21, the open cluster. And Venus is right in between. Again, Venus, just like the moon and Mercury, will present phases to us, and it's a little bit gibbous at the moment. By the way, don't expect to see any detail like this on Venus if you're looking at it for the first time, because this image was taken by the Magellan spacecraft, which was able to see right through the dense layer of clouds that totally envelop Venus using radar. Unfortunately, as I said, none of this detail would be visible in your telescopes. Zooming back out, in the next couple of mornings, there will be something else that happens here. Let's see what happens the morning of Monday this coming week, and something is not playing the game here. So I'll go back out. Here we go. The moon gets very near Venus in 3 days, or is it? Yeah, I think it is in 3 days. Let's check. It'll be on the 12th. So if you want to get there on the morning of the 12th, not only will you have Venus in a photographic opportunity, you shall have a very, very thin crescent moon, plus M8, M20, and M21. However, good luck to you, and may your skill be great enough to be able to capture it. You can't win it unless you're in it. So give it a go and see if it's possible to do. And if it is, place or share your images with the rest of us, and we would be very, very pleased to see them. Now, back to the 9th, and let's go to sunset. We'll go to the northern sky. and a little bit further east, and have a look at a couple of objects that I pointed out to some of our ASV members doing the Learn to Use Your Telescope course last night. The Pleiades, the Seven Sisters right here, is a fabulous object to have a look at with a small telescope. You won't see that nebulosity, but you should be able to make out many stars in there together at the one time in the one field. So that's the Pleiades M45. Over here we have Mesothem, a terrific double star, which kind of looks a little bit like the Kawasaki motorbikes that have twin headlights. This is Gamma Arietis. Both stars orbit around a common center of gravity. Their orientation is exactly north-south, and their magnitude is also exactly the same. So this star is part of the constellation Aries, and what you look for is a very narrow triangle. Here, this star is Hamal, a second magnitude star, which is easy to see and not far from the Pleiades. This is Sheraton, Beta Arietis, and this is Mesothem. Now, Claire earlier was speaking about 51 Pegasi, and if some of you were at the Starbecue back in December at our dark sky site, I pointed out 51 Pegasi just to the west of the Great Square of Pegasus to the people that were there. Hopefully we'll be able to have a look at it again next December when it's up and in a good position to be seen. Oh, there's a satellite going through there at the moment, the Starlink satellite. We can zoom in and have a quick look at that as it moves through. Now, there it is, we're nearly there. There. So that's one of the Starlink satellites. On a number of occasions, you may be able to see a few of them going through the same part of the sky within minutes of each other. But back to here, if we zoom in to the saucepan, here's the handle, there's one side of the saucepan, the bottom of the saucepan, and the other side. These stars are Alnitak, Alnilam, and Mintaka. And right about here is the Orion Nebula, which can be seen with naked eye, but only as a hazy little star. Binoculars will show you a little bit more, and of course, a telescope will give it to you in all its glory. And if you're at a dark sky site, it will look even better. To give you a little bit of an idea of what it's like when you take your 8-inch telescope to a dark sky site, it's a bit like having a 16-inch telescope in Melbourne. That's the sort of difference it makes. Almost doubles its ability to show you objects. In the southern, actually just before I leave here, this fabulous star, catalogued in my old Norton Star Atlas as H3945, is one of the most beautiful double stars in the sky. because you can see these gorgeous colors in them. One of the stars is orangey and the other one is blue. I only know of one other star where you can readily see the colors as well as this, and that is Albireo Beta Cygni in the constellation of Cygnus, visible to us through the winter months and early spring. So the way to find H3945 is to do this. Canis Major, the big dog, is here. This is Sirius. The front leg is there. The dog, by the way, is on its back with the legs up in the air. There's the hind legs and the tail over here. The head of the dog is pointed out by these two stars being the eye and the snout over here. Now, what you do is you take a line from Adhara through Wesson and extend it almost as far again to this star, which, even though here it says it's HIP 35210, it's better known to many astronomers as H3945. Have a look for it. You will need a telescope and you'll make out the beautiful colours. Now let's go to the southern sky to finish up with.
I was just about to give you a 5-minute warning there, Perry. You beat me to it. And I was imaging Canis Major last night with my phone on a tripod. So I might get the telescope out later and try and get that double star.
Well, by all means, your 8-inch will give you a fabulous view of it. So give it a go. As Molly Malcolm used to say, Mark, do yourself a favour. You won't regret it. And then perhaps next time you're at an event of some sort or at the dark sky site, the responsibility falls on your shoulders to share the universe with them and tell them about H3945. So, looking to the south now, we can see Alpha and Beta Centauri, always pointing to the top star of the cross, Southern Cross, which is almost on its head at the moment. The southern Milky Way going through here. The jewel box is right there, but it's probably not in the best position to be viewed. It's much better when the Southern Cross is higher up. However, through here, if we center it and take the time a little bit later, this is the Diamond Cross, and just next to the Diamond Cross, there's a wonderful connection of objects. There's the Eta Carinae Nebula. There's the first object photographed by the Hubble Space Telescope, which is the Open Cluster 3532, also known as the pincushion because it appears like all the stars are holes in this cushion of space with light coming out of them. And also my favourite open cluster, which is 3293, the Pyramid Cluster. But this here is 3532, the pincushion, or sometimes also known as the wishing well, because they look like coins at the bottom of a well, reflecting light back up at you. Fabulous cluster with a couple of nice orange stars in there. Here is the Eta Carinae Nebula, and I must say this is one of the worst photographs I've ever seen of it depicted here. So let's move away from it. But as I said last night to my students, to find the Eta Carinae Nebula, all you have to do is aim your telescope or your finder scope to begin with at the brightest part of the southern Milky Way. That will be the Eta Carinae Nebula, and it is quite a bit brighter and many times larger than what the Orion Nebula is. But it doesn't get as much currency because most astronomers live in the Northern Hemisphere and they've never actually seen it with their own eyes. Were they living in the Southern Hemisphere, it would be the first bit of nebulosity mentioned way before the Orion Nebula. So it's a terrific object to aim a telescope at. And I'll finish with two objects. This is the Pyramid Cluster 3293, because you can imagine it shaped like a pyramid with the corners, the stars in each corner, and then concentric lines moving into the tip of the pyramid, like flying over it in a helicopter. So it is a beautiful little cluster, the Pyramid Cluster. And the final object I will point out is the Cat's Eye double star, which is right next to Achernar. This is Achernar here, and the star is P Eridani. Now, this is not the Greek letter P, and by the way, no self-respecting Greek ever calls that letter pi. A pie is something you put sauce on and you have in front of a football match. This is the Greek letter is referred to as P, much the same as what the English lowercase p is in this case. I will center it and we'll move in to have a look at this double, and it reminds me of my headlights catching my old cat Lucky down the laneway as I came home late in the evenings, because they are distinctly yellow, just like her eyes, and so referred to as the cat's eyes double. Very easy to find because it's only 1 degree away from Achernar, and Achernar, which by the way means the end of the river, is one of the brightest stars in the southern sky, comparable only to Alpha and Beta Centauri, Alpha Crucis and Beta Crucis, and also Canopus over there. They're the brightest 6 stars in the southern sky, and that's where it is. Oh, I forgot, finally, 47 Tucanae, the globular cluster, which is a magnificent object to have a look at. You can pick it up with a naked eye as a fuzzy little star, but here it is as viewed through a telescope. A small telescope will show you a luminous circular patch, and a larger telescope, or if you take that smaller telescope to the ASV's dark sky site, will begin to show you some of the individual stars inherent in this globular cluster. That's it from me. Thank you for your attention. I'll hand you back to Mark.
Thank you, Perry. Whoop. Okay, so it's time for us to do the raffle, Steve.
No. If you wouldn't mind, can we put up the list of new members first before we go through? The list of new members, yes. Let's get that up. Here we go. As Perry mentioned, we had 130 odd new members in the last month, and they all went into this wonderful raffle of a 8-inch Dobsonian telescope, which Perry, with great gusto, found where no one else could find one. Mind you, he had to beg and borrow to get it, but I thank him for his efforts there. And the second prize, of course, is a $500 voucher. So 2 great prizes for our members. That's a very, very tiny list.
I haven't seen a list like this since I joined the ASV. So that's,
no, what I'm saying is I can't read any of it.
That's the best I can do, unfortunately. Technology, hey? We can zoom in a bit. Oh, there we go. How's that?
Okay, so if you're one of the members on that lucky list, we're now going to go into the draw. It's going to be spun twice. The first one will be the major prize, which will be a 8-inch Dobsonian. And the second draw will be for the voucher. So Mark, if you'd like to do the honours.
I will. Hold on a tick. We'll get the new screen up now. Wheel of names. Okay. Are we ready? So this is obviously going to be for the main prize. And let's spin. Lauren Earls, you've won yourself an 8-inch Dobsonian. We'll get our membership secretary to contact you in the coming days. And I should do the right thing and take Lauren out of the second draw because that only seems fair. And let's draw the $500 voucher. Aaron Gillett, the winner of the $500 Celestron voucher. Now just get myself back in here. Stop screen. There we go. There we go. So we have our 2 winners. Congratulations.
We should perhaps think about doing this again next year. And it seemed to be quite fun. We got quite a few new members out of it. That concludes our meeting. The next meeting will be on the February the 9th at 8 p.m. It'll be another meeting like this, a webcast. We haven't heard back from the Royal Botanical Gardens yet as to when we can get back into the herbarium to do face-to-face meetings. So I'm anticipating that this would be another streamed event. Hopefully we could actually stream it and hold it at the herbarium, but we haven't heard anything back yet.
That'd be good.
Next guest speaker for that month will be Ilya Mandel. He's from Monash University, and he's going to be speaking on gravitational wave astronomy. And Claire actually mentioned something about gravitational wave detecting exoplanets. I think it was only 1 or something that was detected, but yeah. So that's next month. And that's all for me. Have you got anything else to say, Mark, to finish off?
Just that we are looking to do a Valentine's Day event. It's still a work in progress. So for those of you who want to spoil your loved one, we'll have a very boutique event coming up on Valentine's Day evening. We're thinking of calling it Wine Under the Stars. And also, Perry, I'm going to work closely with Perry to try and get some public events at the Melbourne Observatory, aren't we, Perry? We're trying to get something happening back there again.
Yes, so, a very central location that we should take advantage of. And also, guys, if I may, just a moment to thank Celestron for their generosity for this voucher. Very nice of them to support.
Was very nice of them.
Thank you.
Wonderful. So keep an eye out for those upcoming events.
Okay. Well, that's it. I hope you enjoyed the program, and we will catch you in the near future next month.
No worries. See you later.
Cheers.
Good night, everyone.